Imagine for a second that you're staring at a screen, right?
Yeah.
And this critical alert flashes in front of you. It's a NOTAM, a notice to airmen, and it reads exactly like this. Quote, AIP updated. Refer to AIC. ATC procedures revised.
Yeah, which means absolutely nothing to most people.
Exactly. I mean, you read it again, right? AIP updated, refer to AIC, ATC procedures revised. If you're, outside the aviation industry, that string of letters probably just looks like a massive typo,
Oh.
or maybe like a software error code.
Oh, totally. It looks completely opaque to the uninitiated,
Right.
but to a pilot or an air traffic controller, that tiny, highly compressed string of characters contains vital, non-negotiable instructions. I mean, it tells them how to navigate the airspace safely.
Right.
There is no room for pleasantries. There are no full sentences.
Well, welcome to today's deep dive. Our mission today is to decode exactly that. We're looking at the highly structured, highly compressed operational language of global aviation. We're breaking down how massive amounts of critical life or death information are shrunk down into these tiny standardized abbreviations, and how those abbreviations actually dictate the physics of flying.
So, okay, let's unpack this. Because if you don't know these terms, you are completely blind to the operational reality of the sky.
Yeah, you really are.
Aviation just doesn't have the luxury of using long, winding explanations. It uses standardized data that acts more like executable computer code than human language.
Right, because in a fast-moving, high-stakes environment like global aviation, eliminating ambiguity isn't just about saving space on a screen. I mean,
No.
when an aircraft is moving at 500 miles an hour, reading comprehension simply takes too long.
Wow, yeah.
There is zero time for interpretation, zero time for nuance. A controller needs to transmit an instruction that is universally understood by a pilot from Tokyo, a pilot from Nairobi, and a pilot from Chicago instantaneously.
Instantaneously, right.
The language has to be as precisely engineered as the jet engines themselves. So let's look at how this engineering works in practice. Because before an aircraft can even communicate its status or, where it's going, the system has to establish the physical environment. It
Exactly.
has to define exactly where everything is on the ground, on the global map, and in the air.
Because you can't navigate if you haven't mathematically agreed on the coordinates of reality. Every single calculation has to be anchored to a fixed truth.
And in aviation data, that fixed truth starts with ADR aerodrome. Now, anyone who flies knows what an airport is, obviously.
Right.
But in these operational documents, an aerodrome isn't just a piece of real estate with a terminal and a runway. Every single procedure fundamentally starts by defining the aerodrome as a mathematical anchor point.
It operates as the absolute 0, 0 coordinate on a grid. When a dispatcher is calculating fuel loads, weight distributions, optimal climb gradients, or even emergency abort procedures.
The really critical stuff.
Exactly. They aren't calculating a flight to London. They are calculating the physical reality of a defined ADR. The elevation of that specific aerodrome, the length of its specific tarmac, the local temperature profile. I mean, every mathematical formula requires an immutable starting variable, and the ADR is that variable.
So we have our fixed point on the ground. But the sky isn't just one big open continuum. The globe is actually sliced up into these highly regulated administrative blocks. And one of the abbreviations we see constantly in the sources is AFI, which stands for the Africa Indian Ocean Region.
Yeah, the International Civil Aviation Organization, or ICAO, divides the entire world into specific navigational regions, and AFI is just one of those massive global grids.
Okay, but if I'm flying at, 35,000 feet, the sky is physically identical, whether I'm over the Indian Ocean or the North Atlantic. So why carve the atmosphere into these invisible geopolitical zones? Like, does a pilot actually have to do something different when they cross from one region to another?
They absolutely do. The physical realities of those regions dictate entirely different operational rules.
Right.
Yeah, procedures vary heavily depending on the ICAO region. Think about the underlying infrastructure down on the ground. Over Europe, you have incredibly dense overlapping radar coverage and VHF radio tracking.
Right, because there are so many airports and cities.
Exactly. You can maintain constant high-fidelity contact. But over the massive expanses of the AFI region or the Pacific Ocean, radar coverage might drop off entirely.
So the pilots are just flying blind.
Not blind, no, but they are relying on different systems, things like high-frequency radio or satellite-based waypoint reporting. And because of that, the rules have to change.
Oh, I get it.
The distance required between aircraft, what they call the separation minimums, might have to be doubled or even tripled in a region with sparse radar compared to a highly congested region.
That makes total sense.
Right. So an abbreviation like AFI instantly signals to the flight computer, the crew, and the controllers that a specific set of regional physics and procedural spacing is now in effect.
So you cross an invisible line in the sky, and the entire rulebook just shifts to compensate for the hardware on the ground.
Precisely.
Now, speaking of the physical environment, we really have to talk about the vertical axis, because altitude isn't as simple as just, how high up are you?
Definitely not.
We have an abbreviation called AGL, above ground level. This is the height measured relative to the specific surface directly below the aircraft. And aviation documentation draws a massive, heavy line between AGL and AAL, which is height above aerodrome level.
And this is one of the most vital distinctions in all of aviation safety.
Really?
Yes, because AAL is localized purely to the departure or arrival airport. But AGL applies to the dynamic terrain you are currently flying over.
Okay, so AGL is like measuring your height from the specific step of the staircase you are standing on, rather than from the ground floor of the house.
Oh, that's a great way to put it.
Right, like if I'm on the 10th step, my distance to the step beneath my foot is just a few inches, even if I'm technically 10 feet above the ground floor.
What's fascinating here is how that hyperspecific definition prevents controlled flight into terrain, or CFAT. Let's apply your staircase analogy to a real-world scenario. Imagine a flight departing from a coastal airport at sea level, and it's heading directly toward a massive mountain range.
Okay.
If that pilot is relying purely on their AAL, their altitude relative to the airport they left 20 minutes ago, they might read 10,000 feet and think they have plenty of safety margin.
But the mountain peaks below them are at like 9,500 feet.
Exactly, which means their AGL, their above ground level, their actual distance to the jagged rock directly beneath the fuselage, is only 500 feet.
Wow. That is a terrifying difference.
It is. By strictly separating AGL from AAL, the operational language forces the aircraft's systems and the pilot to constantly acknowledge the changing, uneven reality of the Earth's crust. Radar altimeters bounce signals off the ground specifically to measure AGL.
Ah, okay.
It strips away the illusion of a flat world and replaces it with your exact relative proximity to danger.
Okay, so we have our 3D grid perfectly mapped out. We know our aerodrome coordinates, we know our regional rulebook, and we know our exact distance to the ground. But knowing where you are is basically useless if you don't know when you're supposed to be there.
That is very true.
Planes aren't static objects. The moment an aircraft pushes back from the gate, we move from the physical grid into the strict, unforgiving domain of time.
And time really is the ultimate metric here. The entire airspace system is basically an exercise in four-dimensional geometry, with time being the variable that keeps aircraft from colliding into each other.
And there is a very specific abbreviation for this, ADT, actual departure time.
And the operational weight entirely rests on the word actual.
Okay, so here's where it gets really interesting, especially for anyone who travels frequently. Like when you book a ticket, your app tells you the flight leaves at 8 a.m. You plan your whole morning around 8 a.m. But operationally, that scheduled time is a ghost. It doesn't exist. ADT is totally independent of what the marketing department or the ticketing system planned. It is the undeniable physical moment the aircraft actually releases its brakes and moves.
Yeah, the schedule time is merely an aspiration. And the global aviation network cannot run on aspirations. It has to run on the actual physics of movement.
Right.
The operations crew, the air traffic controllers, the automated tracking systems, none of them care what the passenger ticket says. They rely exclusively on the ADT because it acts as the trigger for a whole cascade of operational mathematics.
So walk us through that cascade. Why does a minor difference between a scheduled time and an actual departure time matter so much to the whole network?
Well, if we connect this to the bigger picture, global aviation is a tightly choreographed sequence of slots. Every aircraft in the sky is moving through a predefined moving bubble of empty space. If an aircraft's ADT shifts by just 4 minutes, maybe because of a baggage loading delay or a slow tug truck, it doesn't just affect that single plane. The airspace at their destination, say London Heathrow, might now be completely saturated when they arrive 4 minutes late.
Because another plane has already slipped into that arrival window.
Precisely. Which means our delayed plane now has to be placed into a holding pattern. But a holding pattern burns extra fuel, So the dispatcher has to recalculate the fuel reserves based on that new ADT.
Wow, just from 4 minutes.
Oh, it gets more complex. Furthermore, the air traffic controllers along the entire route spanning the Atlantic have to adjust their spacing, perhaps slowing down trailing aircraft to maintain the required separation. A single delayed ADT demands immediate, complex recalculations for tracking and coordination across thousands of miles.
So space and time are locked in. We have our physical location, and we have the exact second the clock started ticking on our movement. But an aircraft moving through space and time still needs to know what it is legally allowed to do. Like, how does a pilot know what rules apply to a pop-up thunderstorm or a sudden runway closure? We move into the strict hierarchy of aviation documents and services.
And this is where we see the absolute boundary between a suggestion and a legal command.
Right. So there are 3 acronyms that constantly show up in the source material: AFIS, AIC, and AIP. Let's break these down, because the distinction between receiving information and receiving an instruction seems to be the core of aviation safety.
It absolutely is.
Let's start with AFIS, Aerodrome Flight Information Service. This is typically used in smaller or uncontrolled aerodromes. The crucial operational distinction here is that AFIS provides traffic awareness and weather updates, but it is explicitly not air traffic control.
Exactly. It provides situational awareness, but it holds zero authority to dictate the flight path.
It gives no control instructions. Then we have AIC, Aeronautical Information Circular. This is a document that contains informational content, administrative advisories, maybe long-term policy updates, but it specifically does not contain operational instructions.
Right. It gives you context about the regulatory environment, but it does not tell you how to fly the plane.
And finally, we arrive at the foundational document, AIP, Aeronautical Information Publication. This is the absolute core of a nation's airspace rules. It contains the hard procedures, the finalized airport data, the permanent airspace structures. Every single aviation professional must operate within its parameters.
Unconditionally.
So what does this all mean? To me, it sounds like, well, AIP is the criminal code you absolutely must follow to avoid going to jail.
Yeah.
AIC is like a city council newsletter telling you they might change the parking rules next year. And AFIS is like the traffic reporter in a helicopter on the morning news.
That is a highly functional way to look at it, actually.
Yeah.
Let's take the traffic reporter analogy. The AFIS operator can look out the window of a small regional tower and tell a pilot on the radio, be advised, there is a flock of birds near the end of the runway. Or there is another Cessna on a downwind leg. But they cannot legally say, turn left to heading 240 and hold short of runway 9.
Because they aren't air traffic control.
Right. And the reason this hierarchy exists, the reason the operational language rigorously isolates an AIP procedure from an AIC advisory, comes down to liability and predictability.
Liability, okay.
In aviation, whoever holds the authority to issue an instruction also holds the liability for the safety of that instruction. If air traffic control orders a pilot to descend at 3,000 feet, ATC has already verified on their radar that the airspace is clear. They hold the liability.
And the AFIS operator doesn't have that.
Right. An AFI operator in an uncontrolled aerodrome does not have that comprehensive radar picture.
So if a pilot treated AFIS advice like an ATC command, they might blindly turn into the path of another aircraft, assuming the AFIS operator had already cleared the airspace for them.
Which would be catastrophic. If you blend helpful advice with mandatory instructions, the pilot loses the understanding of who is actually managing the separation of aircraft.
Right, the roles get entirely blurred.
Exactly. So by strictly categorizing AFIS, AIC, and AIP, the system guarantees that a pilot knows exactly when they are independently responsible for avoiding traffic using information and when they are legally bound to follow a controller's command.
Wow. Okay, so we have our locations mapped, we have our exact reality-based timing, and we have a ruthlessly categorized set of rules dictating who holds the authority at any given moment. But how does all this data actually travel around the world? I mean, a delay in ADT in Tokyo needs to be known in Los Angeles instantly. We are talking about the physical networks that carry this data.
Yeah, because you cannot operate a globally synchronized system without a dedicated global nervous system to transmit the impulses.
And there are 2 abbreviations that define this infrastructure: AFS and AFTN. AFS is the Aeronautical Fixed Service. It is the overarching telecommunications architecture that connects airports, control units, meteorological stations, and operational centers.
It acts as the broad physical infrastructure, the subterranean cables and satellite links dedicated to moving aviation data.
And running inside that infrastructure is AFTN, the Aeronautical Fixed Telecommunication Network. This is the specific messaging system used for flight plans, for NOTAMs like the alert we talked about at the very beginning of the deep dive, and for urgent operational messages. It operates as the messaging backbone of the entire industry.
It is the single most critical pipeline for operational truth.
But wait, this raises a really big question for me, though. We live in an era of hyperconnectivity. We have fiber optics, 5G, and a massive global internet infrastructure. Why does aviation need its own entirely separate, highly rigid network like AFTN just to send what is essentially a text message containing a flight plan or an AIP update? Why not just use heavily encrypted internet protocols?
This raises an important question. It really does. Because standard internet protocols prioritize efficiency of routing over the absolute guarantee of delivery.
Oh, interesting.
Think about how the public internet functions. When you send an email or stream a video, the data packets are broken up and dynamically routed through whichever global pathways are currently least congested. If a packet gets dropped, the protocol simply requests it again. You experience a split second of buffering, or an email takes an extra 30 seconds to arrive.
Which is totally fine for daily life.
But it is completely unacceptable when routing a NOTAM about a closed runway. AFTN operates more like a hospital's closed-circuit life support paging system, whereas the internet is like public cellular data.
Right.
AFTN uses dedicated circuits and message switching protocols that guarantee a message is pushed to its exact destination in a specific order.
It strips away all the bloat.
Entirely. There is no HTML, no heavy metadata, no dynamic rerouting delays. The messages are purely alphanumeric, strictly formatted strings of text. If a critical piece of airport lighting fails in a remote AFI region aerodrome, that alert cannot get stuck in a server queue behind millions of civilian streaming requests.
Because lives are literally on the line.
Right. It has to instantly trigger alarms on the screens of every relevant dispatcher and air traffic control center globally. AFTN ensures that operational data never competes with civilian bandwidth. The aviation industry engineered a parallel internet that prizes absolute reliability and guaranteed delivery times above everything else.
That is just incredible. It fundamentally changes how you perceive the mechanics of air travel. The next time you board a commercial flight and you're sitting at the gate waiting for pushback, look out the window. You aren't just sitting in a complex machine.
No, you're not.
You are suspended in this massive, invisible mathematical web. A web driven by actual departure times, forcing instantaneous global recalculations, carried across dedicated AFTN networks, firing off guaranteed data packets in milliseconds, all operating under rigid AIP procedures that dictate every invisible corridor in the sky above you.
And it achieves that unprecedented level of global safety precisely because the communication is engineered to be completely devoid of human ambiguity. It operates exactly as it was designed: short, precise, global.
Which leaves a really provocative thought to ponder after this deep dive wraps up. We've just explored how this ruthlessly compressed, standardized language, a language intentionally stripped of all emotion, all nuance, all subjective interpretation, is the only mechanism capable of keeping millions of flights perfectly safe across different cultures and continents. So what would happen if we attempted to force our everyday human systems to operate with this exact same level of standardized, unforgiving efficiency?
You mean applying AFTN-style formatting to human interactions?
Exactly. Imagine if our legal contracts or our political debates or even just our everyday internet discourse were restricted to this kind of operational syntax. Short, precise, zero ambiguity.
Wow.
On one hand, would it completely eradicate our endless communication breakdowns and societal misunderstandings? Or, by stripping away all that nuance, context, and emotion, would we essentially strip away our humanity in the process?
It highlights the ultimate tension between the desire for absolute operational perfection and the messy reality of human expression.
It really does. Well, thank you for joining us on this deep dive. Keep questioning the invisible systems operating all around you. And the next time you see a wall of letters that says AIP updated, refer to AIC, you'll understand the massive global infrastructure required to deliver that single life-saving sentence.